For part J, says the student notices that the rightmost peak of O is taller than that of P. They claim that this is because O has fewer occupied shells, which means that the valence electrons are closer to the nucleus and experience greater attraction. Do you agree or disagree with the student's claim? Justify based on the data and principles of atomic structure. Okay, so while this statement is true, that O has fewer occupied shells and that the valence electrons are closer to the nucleus because they experience greater attraction, that does not explain why the peak in O is higher than the peak in P, okay? So remember, the height of the peak, the y-axis, is related to the relative number of electrons. So if you look at the last shell of O, it's based on the peak, 1s2, 2s2, 2p4. If you look on the peak of P, or the electron configuration of P, it's 1s2, 2s2, 2p6, 3s2, 3p3. So since there are only 3 electrons in that last shell of P, that's why the peak is lower, not because of the distance based from the nucleus. So remember the binding energy, that's what's going to be related to the greater attraction to the nucleus. That's why it takes a little bit more energy to remove O's electrons than P's electrons. Okay, so that one was tricky because what he says is correct. It's just his reasoning for the peak is wrong, so that's why you disagree. For sample question 2, write the chemical formula of a species that behaves as a catalyst in the mechanism. So remember, the catalyst is going to be consumed and then produced somewhere in the equation. So looking at those two, looking at the reactions, we have CH3OH consumed in the first step and then produced in the second step. So CH3OH is going to be our catalyst in this mechanism. Part B, according to the proposed mechanism, if NH3 is added to the mixture, will the rate of the overall reaction increase, decrease, or remain the same? Justify your answer. So looking at NH3 is a part of step 2. The only thing that's going to change the rate of the overall reaction is if we affect the slow step, because remember the slow step is the rate determining step. So if we add NH3, the rate of the reaction will remain the same because NH3 is part of a fast step, not part of the rate determining step 1. Part C, is the student's diagram consistent with the enthalpy of the overall reaction? Justify your answer. The enthalpy of the overall reaction is negative 81 kilojoules per mole. So I'm going to say no, it is not consistent with the enthalpy of the overall reaction. Since it is a negative enthalpy, that means it's exothermic and energy is released. So the potential energy of the products should be lower than the potential energy of the reactants. So you should basically flip those bars. Then we have part D, identify all the types of intermolecular forces in HCOOH and CH3OH. These two molecules actually have the same intermolecular forces. So if we look at HCOOH, it experiences London dispersion forces, because everything does. It experiences dipole-dipole forces between that C and O, or because of that C and O bond. And then we also experience hydrogen bonding because of that OH bond. If we look at CH3OH, it also experiences London dispersion forces, because everything does. There is some dipole-dipole forces going on between that carbon because of that carbon and oxygen bond, not between, it's only between different molecules, not within a molecule. And then we also have hydrogen bonding because of that O bonded to that H. E, when an equimolar mixture of the two compounds is heated, the vapor phase contains a higher mole fraction of CH3OH molecules. Explain this in terms of the types and relative strengths of intermolecular forces in both substances. So because they have the same types of intermolecular forces, this is going to be based purely on the strength of those intermolecular forces. So that means that the strength of intermolecular forces for CH3OH molecules is much weaker because they go into the vapor phase easier than the HCOOH molecules. This can be explained because HCOOH has a higher polarizability, meaning that that is going to increase the strength of dispersion forces present because it has more electrons present in the molecule than CH3OH. Okay. Then we're on to part F. We want to calculate the molarity of HCOOH for the student's data from trial 1. So this is the titration problem. Based on the chemical equation, we have a 1-to-1 ratio between OH and H. So the H comes from acetic acids, HCOOH, and the OH comes from sodium hydroxide. So we're dealing with trial 1 here. We know that we have dispensed 16.67 milliliters of OH. And they go to an endpoint, right? Yep. So we're going to take the concentration, which is 0.3 moles of NaOH per 1 liter, and multiply by this volume, which if we convert to liters would be 0.01667 liters. Our liters is going to cancel, and then we're going to get moles for that reaction. Sorry, had to grab my calculator. So that tells me that we have used 0.005 moles of OH minus. Okay. In this titration, there is a 1-to-1 mole ratio between our base and our acid. So you can multiply that by 1 mole over 1 mole to figure out how many moles of H plus were consumed. So that means we use 0.005 moles of H plus. Then we have to divide, to find the molarity, the concentration, we have to divide this 0.005 moles by the volume of our acid, which was 20 milliliters, which is 0.02 liters. When we find out that, we find out that the concentration of our acid is 0.25 molar. Okay, so that is our answer to part F. Part G, the final reading is shown in the experimental setup. What should the student report as the volume dispensed for trial 3? Clearly show the final reading from the burette and the calculation of the volume dispensed. Okay, so for this one, we have an initial burette reading of 1.12 milliliters, according to the data. Then looking at that picture, remember you read a burette from top to bottom. So it looks like I've definitely used I'm at 18. I'm definitely at 18.1, and then I have to estimate one more digit. So I estimated that last digit to be 8. So my ending volume is 18.18 milliliters. You have to report 2 decimal places. You only report 1, you lose the point for significant figures based on experimental instruments. So to find the amount that was dispensed, I take my final minus my initial, and I get 17.06 milliliters. If you estimate this digit to be 9, 7, 6, whatever, that is totally fine because it is an estimated digit. So you may get something a little bit different, but you should have gotten around 17.06 milliliters. Then we come to part H. The student calculates the value of the concentration of this acetic acid that is significantly higher. They claim that the reason for this is that water remained in the flask to which the weak acid was added, which meant more OH was needed to reach the endpoint. Do you agree or disagree with the student's claim? Justify your answer. You are going to disagree. Water is not going to affect this because it is based on the number of moles between OH and H+, the actual reaction that occurs. So it's only based on those moles. Adding water does not affect the moles, okay? So it might affect the concentration a little bit because the volume is going to change, but the number of moles of those do not change. So it should not affect. So water does not change the moles of the acid, just the volume. The number of moles of NaOH needed to neutralize the acid would be the same if the flask is wet or dry. This does not explain why a greater volume was needed in trial 2. And you don't have to come up with another explanation for why it might be or whatever. Just know that no, you would disagree because it would affect, it's only based on the number of moles because that's what the chemical reaction is set up, a reaction between the number of moles of those reactants. Okay, so that is the end of the practice exam. Let me know if you have any other questions and have a great day.